All right, so last time we covered a section, we did 10.2. It was quite a while ago before break, so we reviewed it. Now we're going to take a look at 10.3. Okay, inscribed angles. So inscribed angles basically have to do with drawing something inside of a circle, whether it's just an angle or an entire polygon. Okay, we're going to look at both. So basically, an inscribed angle is an angle whose vertex is on the edge of the circle, and the sides of the angle are chords. Okay, so let me make a sketch. So there's going to be my vertex. That's going to be on the edge of the circle. And there's two chords that make up the sides of the angle. That's an inscribed angle, what I just drew. And the two sides of the angle are chords. I also created an arc right here. Well, there's a special connection between that arc in green and that angle. I'm going to tell you what it is in a second. But this angle in green is called an intercepted arc. It's where the two sides of the angle intersect the edges of the circle. Okay, and if you want to write all that down, if it helps you, that's great. If you just want to make a picture and label it with those words I've underlined, that's just as good. Okay, so that's the intercepted arc. That's an inscribed angle. Okay, any questions on what an inscribed angle is or an intercepted arc is? Anybody think they know what the connection is going to be between the size of the angle and the size of this arc? Well, we learned when you have a central angle, it's the same. Or if we didn't learn that, we will learn that. Okay, but if you've got something like this, draw that. That arc and that angle are exactly the same. These aren't the same. Yeah, the arc is going to end up being double. Or you could say the inscribed angle is half. Right? So if this inscribed angle is 30, the arc is 60. Okay? That's the connection. Okay, so that idea that Luke just explained, that's Theorem 10.8. For me, it's most helpful to just look at the picture rather than all the words. But the idea is angle ADB is half the size of arc AB. That's the connection between an inscribed angle and an intercepted arc. The inscribed angle is half the arc. And we can use that idea both ways. If I gave you the size of the arc, you could take half of it and figure out the size of the angle. Or if I give you the angle, you could double it and find the size of the arc.
Mr. Hager, let's say just like a regular angle, right? Like, let's say it's like 156 degrees or something like that, and you just kept going with the lines. Would that angle just grow? Or would the arc for that angle just grow? You just kept going to the other side?
With the arc, no, the arc would still be the same measure.
Then how come it's not the same for this? Like, why isn't the inscribed angle the same as in intercepted arc?
Well, remember we talked about, let me show you an example. We had concentric circles.
Yeah.
Okay, kind of like this. And if I mark the center, okay, draw in an angle. This arc and this arc are exactly the same measure. Because the way you measure an arc is based off of that angle. And they're both based off the same angle. So those arcs would be the same size. It goes back to a theorem. I think it was in 10.1 or 10.2. I understand what you're saying. This arc is, like if you were to draw it, it's a bigger arc than this one. It's longer, like if you would take a piece of string and measure it. But we're not measuring the length of the arc in like inches. We're measuring it in degrees, which is different.
So, but still, if I had, can I just like show you what I'm talking about?
Yep.
Like, never mind. It's just like, I was gonna say, if you have like an angle like this, and that's like 156 degrees or something like that, and
yep.
if I just kept going, would that still be 156 degrees?
Yes, the arc would still measure 156 degrees. I agree with you, it is longer, but it's the same angle
But
measure.
how come that, or whatever it is not the same as, you know, like, why is that double the inscribed arc angle?
Why is this arc double the size of this angle?
Yeah.
Well, we'd have to prove that theorem to do that. I wasn't going to go through the proof today, but we could prove it. That's just the connection between angle size and arc size. And Luke, it doesn't matter what size picture you have. Like, let's say we had this. Okay, let's take this. Let's make a angle right here. Let's do that. Now let's take the same picture. Let's make a bigger version of it. Let's group that all together. These two angles, exactly the same. Right? Even though this angle has longer chords, it's still the same measure as that one if you use a protractor. And since the size of this arc only depends on the size of this angle, these two arcs are exactly the same measure in degrees.
Oh, so you're talking about okay.
Yeah.
Degrees. Okay.
In degrees.
You're talking about.
I agree with you. If you took like a piece of string and you measured it, this arc is going to be longer.
Oh, okay.
No, there's no doubt about that.
You just make it look stupid, Mr. Hager.
But
Thanks.
no, does it make sense?
It's not very hard to make it look stupid, granted, but you know.
You're not, you got it?
Okay.
Do not put yourself down.
So if you take trig, there's a difference between the measure of an arc in degrees and the length of an arc in inches, if you take a piece of string and measure it.
Centimeters.
Yeah, two different things. Okay, so let's find the measure of the arc in red, right there. Remember, we're measuring it in degrees. Anybody think they know what would the arc STQ come out to? Okay, so if you're not sure what the arc is, first figure out the measure of angle R. Then try to remember the connection between the size of the arc and the size of the angle. Connor? Yeah, the arc would be 180. Because the inscribed angle is 90. This angle is half the arc. Okay? So double the angle, you get the size of the arc. So what would that mean if you connected S and Q?
The right triangle.
Okay, you have a right triangle, and SQ would be a hypotenuse. What else would SQ be in this circle?
A chord.
The diameter.
It'd be the diameter. Right? Okay. Anytime you've got a segment, and that segment creates an arc of 180 degrees, okay, where it intercepts, it's got to be the diameter. Okay, it has to go right through the middle. Okay. We'll use that idea in a little bit, like if I wanted to find the length, maybe knowing SQ is a hypotenuse or a right triangle, that would help us out. But we'll get to that. Okay. How about arc ZWX? Or how big is that arc going to be?
230 degrees.
Yeah, 230 degrees. Okay. Your arc is going to be double the size of your inscribed angle. Okay. Remember, for an angle to be inscribed, it's going to have its vertex right on the edge of the circle, and the two sides of the angle are chords. Any question on B? Okay, so it's pretty straightforward theorem to use. Let's try it the other way. Now, this time I want to find the measure of angle M. So arc NP is 100 degrees. What's the measure of angle M here, Sarah? 50. Okay. The size of your inscribed angle is half the intercepted arc. Okay. Any question on theorem 10.8? Okay. This problem is going to lead us to theorem 10.9. I want to find the measure of angle ACB. Okay, start with that. ACB. Okay. Anybody think they see what that is going to come out to?
30.
Yeah. Okay. Angle C is an inscribed angle. The intercepted arc for ACB is 60 degrees. So it's half of it. It's 30. How about the measure of angle ADB? ADB. Yeah, that's also 30. This time, D is the inscribed angle. Look at the two lines in black. The intercepted arc is AB. It's the same as the intercepted arc for the two lines in red. How about the measure of angle AEB?
30.
Yeah, that's also 30. AEB, that's the two lines in green. Okay. Angle E is the inscribed angle. Look at the intercepted arc for the two lines in green. It's 60 degrees again. Any questions why all three of those angles came out to 30? Okay, they all have the same intercepted arc. So that leads us to the next theorem, which is if two inscribed angles intercept the same arc, then the angles are the same size. They're congruent. All right, so in this case, if you look at angle C and angle D, angle C and D, inscribed angles. C intercepts arc AB. D intercepts arc AB. Both C and D have the same arc, so the angles are congruent.
So C and D, the
Yep.
arc of C and D.
Yep, in fact, I'll do it. So look at the two lines in blue. Okay, that's C. The two lines in blue make an arc just like that. Now, look at the two lines in red. Look where they intersect.
Yeah, I understand that part, but what if we were doing
Same arc.
the arc of CD?
Arc CD, yeah. You could look at it that way too. Okay. There's another arc over here. Okay. Angle A intercepts arc CD. Angle B also intercepts arc CD. So angles A and B are also the same size. Yep. Okay. Any question on that theorem? Okay, so two inscribed angles, if they intercept the same arc, they're congruent, same size. Okay, so I think sometimes, like on a test, it might be helpful to draw it in different colors. And if you have a colored pencil, because if you start getting a lot of lines going, it can look confusing. So I'll try to do that when I can. Okay, I'll try to make it like a different color. Does everyone have what's on the left so I can make what's on the right a little bigger? All right, so they're telling me that angle E is 75 degrees. How big is angle F? Well, let's start and see if we can just figure out what's the intercepted arc for angle E. Tell me the two letters that the sides of that angle hit. GH. So this is your intercepted arc. Look at angle F. What are the two letters that the sides of angle F hit? GH again. So both E and F, they intercept the same arc. So what's the measure of angle F? Yeah. Two angles that intercept the same arc, GH in this case, have the same size. Okay, now, if I gave you a little bit more information, you could find some of these other angles. Like if I gave you H, if you know F is 75 and you knew H, and you know all the angles have to add up to 180, you could figure out this vertical angle at the top, and then it's congruent to that other vertical angle. So there's all kinds of things you could figure out. But any question on how we got angle F? So now, instead of just drawing a single angle inside a circle, we're going to draw an entire polygon. And if you can draw a polygon so that all the vertices of that polygon lie on the edge of a circle, we say that that polygon is inscribed inside a circle. Okay, and I think I have a picture. You don't have to solve those yet. But these are examples of inscribed polygons. All their vertices are on the edge of the circle, and the circle completely contains the entire polygon. So there's two ways you can say it. You can say the polygon is inscribed inside the circle, or you can say the circle goes around the whole thing. It circumscribes the polygon. Okay? Any question on what an inscribed polygon looks like? All right. So now, we've already seen this a little bit. When you draw a right triangle inscribed in a circle, let me do that. Okay, so here's our center. I'm going to draw in one side. What do we know happens all the time? If you draw a right triangle inscribed in a circle, the hypotenuse of that triangle is automatically going to be what?
Diameter.
Yeah, it's going to be the diameter, because it's going to be intercepting an arc of 180 degrees. And that's part of what this theorem says. Okay, so if you draw a right triangle inscribed in a circle, the hypotenuse is the diameter. Okay, that's the first part. The hypotenuse is the diameter. And you can also say it with the converse. If you draw a triangle in a circle and one of the sides is the diameter, then you automatically just made a right triangle. I don't care what else you do. If you drew this picture, you can put another vertex anywhere you want on that circle, as long as it's not the endpoints. Okay?
Does that have to be one vertex or could it be two?
It's, well, for a triangle, just one more. Okay? I don't care where you put it. Okay, no matter where you put it, you're going to create a right triangle. Okay? I had it at the top before. Now I'll put it over here. It doesn't matter where you put it. If one side is the diameter, you automatically just created a right triangle. And the angle that's across from the diameter, that's the 90. Because it's half of the intercepted arc. And the intercepted arc, if you draw a diameter, is always 180. What's the angle across from it? Half as big, 90. Okay, so that's theorem 1010. It has to do with specifically just drawing a triangle, a right triangle, inside a circle. Here's another picture. Okay, in this case, AC is the diameter. That means angle ABC has to be the 90. The 90 is always across from the diameter. Okay, any question on theorem 1010? You almost don't even need to know that theorem if you understand the idea that if you draw in an angle, the intercepted arc is twice as big as the inscribed angle. You can just automatically remember it kind of from that. Okay? Or you can memorize this theorem. And the only other special shape we're going to draw inside a circle is a quadrilateral. Okay, so we'll do triangles and quadrilaterals. So if you wanted to inscribe a quadrilateral in a triangle, you could do it like this. That would work. Something always has to be true, though, for it to work. Does anybody know what has to happen? It's a little tricky.
With the two chords.
Well, your quadrilateral, it's always going to be 4 chords that make up the sides.
No.
It's a special relationship between the angles that are across from each other. Okay. In an inscribed quadrilateral.
Well, couldn't you also have a trapezoid that is a
Could you do a trapezoid?
that has that's the diameter of
Let's try it.
well,
Let's try it, see what happens. Okay, the main thing that has to happen, if you want to draw a quadrilateral in a circle, opposite angles have to add up to 180. If they don't add up to 180, you won't be able to draw a circle going through your 4 points. Okay, here's another example. Like that, kind of looks like a trapezoid. 2 sides that are parallel. It's kind of a trapezoid on its side.
you could also have the points in the diameter, correct?
Oh, you want to put a line through the diameter?
But that also
Well, we'll try it. Let's see if we can do it that way. You can do it as long as your opposite angles come out supplementary, meaning they got to add up to 180. So in this case, D and F have to add up to 180, so do E and G. If they don't add up to 180, it's not going to work. All right, so Connor, you said to draw a line through the diameter, or through the center?
yeah.
Okay, so there's a segment through the center. And you could definitely make a quadrilateral out of that. You just pick two other points, like that, and now connect them all. So that'll work. I don't think that's a trapezoid, but it works. And with just this information, you wouldn't be able to figure out the size of any of these angles. All we really know here is this arc is 180 degrees. That's all I know. Okay, any question on that theorem? So that's going to be our last theorem. We'll try a couple of problems and we'll finish up with this one. Okay, so let's find the value of each variable. What do you know about angle ACB here? There's something special about it.
Isn't that 90?
Right, we know it's a 90. Okay, how do we know that? It's across from a diameter. Any inscribed angle that's across from a diameter is always 90, because the diameter has an intercepted arc of 180, and the angle is half as much. Right, so we know that this angle is 90, angle ACB. So what would x have to be? Katrina? Yeah, x is 45. Okay, angle ACB has to be 90, so find a number for x that when you double it, you get 90. Okay, 45. All right, so this one. This one has to do more with the quadrilateral. Connor, what did we say about opposite angles in an inscribed quadrilateral?
They have to be something.
They have to be supplementary. And what does supplementary mean? They add up to
180.
180. So I know angle D, or the measure of angle D, plus the measure of angle F. Those have to add up to 180. And the measure of angle Y, plus the measure of angle E, also has to add up to 180. Okay, so fill in what you know. You know the measure of angle E. You know the measure of angle F. We can easily find how much D and Y are. Okay, let's start with the first one. Measure of angle D, measure of angle F is 80. So how much is the measure of angle D? Yeah, it's 100. Or in other words, we could say, what did they want us to really say? Z. Z equals 100. How about, oh, this was angle G. Sorry. How much is Y going to be, which is the measure of angle G? 60. Okay. G and E have to add up to 180. E is 120. G's got to be 60. Okay. So the measure of angle G, which they're calling Y, Y is 60. So Z is 100, Y is 60. Okay, any question on that one? Okay, so that's pretty straightforward. When they give you 4 angles and you know 2 of the consecutive ones, it's very easy to find the other opposite ones. Okay, this one's a little harder. This time you don't know any of the angles. You just have an expression for each one. But what I do know is this is a quadrilateral. I know it's inscribed in a circle. So who can tell me 2 equations here that would have to be true? What plus what is going to add up to 180?
3y plus
Okay.
3x
3y, yep.
has to equal 180.
There's one equation. Somehow, 3y plus 3x has to add up to 180. What's another equation?
2y plus 5x has to equal 180.
2y plus 5x has to equal 180.
Can we set up proportion?
For this one, we can't set up a proportion, but we can do something else. Okay. How many variables do we have to solve for? 2. How many equations do we have? 2. We're good. As long as you have as many equations as you do variables, you can figure it out. All right. And this is something we did back in Algebra 1, solving 2 equations for 2 variables. This is called a system. Okay, so this is a system of equations. Okay, one way to solve a system, not the preferred way, is you can get y by itself, get it in y equals mx plus b form. These are basically going to be lines, if you draw them. You could draw this one, draw the other one, and look where they cross. Wherever these 2 lines cross each other, that's the answer. Graphing's kind of a pain, though. Okay, it takes a while. We're going to have some big numbers, so we'll stay away from graphing. Okay, another way we can do it is substitution. Take one of these equations, get y or x by itself, and plug it into the one below it. How many people remember doing something like that with substitution last year? Okay, so we could do that. Or we could multiply everything in the top equation by something and everything in the bottom equation by something so that we make the numbers in front opposites. They don't both have, just one of them. I think that might be the easiest way to do it. Anybody see something we could multiply everything in the top by, multiply everything in the bottom by, so we could make these two numbers opposites, like 5 and negative 5. Okay. We're going to try to avoid using fractions. Okay, first thing we should decide is, do we want to make the numbers in front of y match up or the numbers in front of x? Alyssa, I'll let you pick. Okay, we're going to make the numbers in front of y match up. Okay. Anybody think of a number that 3 and 2 both divide into evenly? That's going to be the number we're going to shoot for, 6. Okay. So somehow we want to make the top one a 6, and we want to make the bottom one a negative 6. If we can do that, they'll cancel each other out. Okay. What could you multiply the top equation by? Yeah, double everything in the top equation. So we'll say double, let's call this equation 1, equation 2. I'm going to write double equation 1. 6y plus 6x equals 360. What about equation 2? We're going to multiply that by. Well, keep in mind, our goal is to get a negative 6 in front of y. Trying to get opposites. This method, by the way, this is called elimination. Okay, that's how we're trying to solve it. Yeah, multiply. In fact, I'll write that down. Multiply the second equation by negative 3. Okay. A number circled just represents the equation I'm talking about. Denver, what do you get when you do that? Yep. Yep, so I'm just going to say minus 15x, and then 180 times negative 3. Or think of 18 times negative 3 and add a 0. Yep, and then add a 0. Negative 540. Good. Okay. So we doubled equation 1, multiplied everything by 2, multiplied everything by negative 3. And now I'll just write these equations close together. Now you add them up. What happens when you take 6y minus 6y? What do you get? 0. The y's are gone. Now we don't have to think about them. Okay. 6, take away 15. What's 6 take away 15? Oh. If you did negative 6 take away 15. Negative, I think someone did, yeah. Negative 9. Okay, now we've got 360 minus 540. Let's just use the calculator. Okay, negative 180. Last step, divide each side by what? Not 9. Negative 9. Good. So that cancels that and that. And that. Okay, so 180 divided by 9, 20. Okay, so we have x equals 20. They want the measure of each angle. Well, there's a couple ways I could do it now. What other letter do I still need to solve for? I still need to know y. But if I know x, I can figure out angles C and B, and then I can figure out the angle across from it because it has to add up to 180. Right? If all they wanted me to do was find y, now that I know x is 20, I would just fill it in right there. And I'd write 3y plus 60 equals 180. Okay? But let's just find the angles. Let's start with B and C. Okay, James, if x is 20, how much is angle B? 60. Okay, Tanner, if x is 20, how much is angle C? 100. Now, if we know angle B is 60, remember the relationship between D and B, they have to add up to 180. So B is 60. How much is D? Connor?
120.
Yep, D has to be 120. Which, if you really wanted to know, that means y is 40. 40 times 3 is 120. Now angle C was 100. Angle A has to be 80. Okay, so from Algebra 1, if you're a little rusty on solving system of equations, you might want to look that up. Okay. If you don't like elimination, you don't have to do it this way. You could do substitution. I would not recommend graphing. It's not going to work well. All right, so the homework, it's on 616, 2 to 8 all, 9 to 25 odd, 35, 42, 43.